We will first discuss some very basic magnetic principles. What happens when current flows in a conductor? What is flux and how is it generated? How is a force produced that moves a conductor? And finally, what happens when a wire or conductor is moving in a flux field? Everyone has had experiences with magnets. Attraction and repulsion are two basic principles of magnets. Magnets have north and south poles. Unlike poles attract each other, while like poles repel each other. Magnetic flux refers to the flow of lines of force between two poles. Flux lines of force always flow from the north magnetic pole to the south magnetic pole. When current flows in a conductor, there will be a rotating magnetic field surrounding the conductor. The direction of the magnetic field can be determined using Maxwell's right-hand grip rule. This rule states when the right-hand thumb points in the direction of the current flow in the conductor, the gripped fingers will indicate the direction of the magnetic field. The rotating magnetic field reverses when current flow direction reverses. If electric current flows through a conductor, a magnetic field will surround the conductor. When wound into turns, the magnetic fields are superimposed. This is known as an electromagnet. The resulting magnetic field is similar to a bar magnet where there is a north pole and a south pole. As with a bar magnet, the electromagnet magnetic field flows from the north pole to the south pole. There are three ways to increase the magnetic flux of an electromagnet. First, increase current. Second, add more turns. And 3, wrap the coils around an iron core. Ferromagnetic materials act like conductors of magnetic fields, offering a path of low reluctance. Much like a conductor provides a low resistance path for current to flow. One of the biggest advantages of working with magnetic fields is that their path can be reshaped and guided using ferromagnetic materials. This is why all types of electric motors and even generators rely on ferromagnetic materials to direct the magnetic field lines in a controlled and desirable manner. When a conductor carrying current is placed in a magnetic field, a force will be applied to the conductor. The conductor rotating flux field and the stationary flux field interact. This interaction produces a force that is perpendicular to the lines of force. It's important to note that the direction of the current flowing through the conductor and the direction of the magnetic field determine the direction of the force. The direction of the force is determined by applying Fleming's left-hand rule. This rule states, if you stretch the thumb, forefinger, and middle finger of your left hand at right angles to each other, pointing the forefinger in the direction of the external magnetic field, and the middle finger in the direction of current in the conductor, the thumb will indicate the direction of the force acting on the conductor. Here, the current direction has changed. Therefore, the direction of force on the conductor has also changed. As shown, the rotating field above the conductor is in same direction as the flux field, so it strengthens the flux field. Below the conductor, the rotating field is in opposite direction of the flux field, which weakens the flux field. The result is a force applied on conductor in the direction of the weakened flux field or downward. You can think of the lines of force like rubber bands. They are always trying to shorten themselves. A coil has two sides. Current flows in one side and out the other. When placed in a magnetic field, there will be a downward force applied to the right coil side and an upward force applied to the left coil side. So that's it. The coil starts to spin. It's perpendicular forces that cause the coil to rotate. Now let's discuss what happens when a conductor travels in a flux field. Faraday's law states that when a conductor is exposed to a changing magnetic field, a voltage is induced in the conductor. The voltage is proportional to how fast it is moving as well as the level of the main field strength. The voltage will only be induced in the conductor if it is cutting across lines of flux. The induced voltage is called counter-electromotive force, CEMF. If a conductor is moved through a magnetic flux field and does not cut lines of force, there will be no voltages induced into the conductor. In this example, the conductor is moving parallel with the magnetic lines of force and not cutting lines of force. Therefore, there is no voltage induced into the conductor. Counter-EMF as it relates to speed control and torque output is a very important topic. In this slide we see that the counter-EMF developed in the conductor opposes the voltage applied to the conductor. When voltage is applied to a motor, rotation occurs. The conductor is rotating in a flux field. Therefore a counter-EMF is developed that opposes the applied voltage. The difference in the applied voltage and the counter-EMF is the voltage used to drive current in the motor.